In this video, we're going to review power series. This is from section 6.1 of the textbook. So let's go ahead and start looking at problem number 1 here. And it's series indexed from n equals 1 to infinity of -1 to the n over n, x to the n. So that's an alternating series there. And they want us to find the interval and radius of convergence for the given power series. So I'm going to use the ratio test here, limit as n goes to infinity, the absolute value of -1 to the n plus 1, x to the n plus 1 over n plus 1 times the reciprocal of this is -1 to the n, x to the n, and then n up here. Now the -1 to the n and the -1 to the n plus 1 don't matter because I'm taking the absolute value, so the sign changers are just going to go away. So I only need the limit on the part that contains the n's, n over n plus 1, and then absolute value bars around x to the n plus 1 divided by x to the n is going to just be x. This all needs to be less than 1 for convergence. And the limit as n goes to infinity of n over n plus 1 is 1. So absolute value of x is less than 1. My radius of convergence there is 1. And x has to be between -1 and 1. Testing the endpoints here. If x is 1, then this is -1 to the n over n, which is conditionally convergent. If x is -1, then this is 1 over n, which is divergent. So my interval of convergence here is going to be -1 not included to 1 included. Let's go ahead and look now at number 3. And it says series from n equals 1 to infinity of 2 to the n over n x to the n. So we'll again use the ratio test. It's not like me writing infinity. There we go. 2 to the n plus 1 over n plus 1 x to the n plus 1 times, and then the reciprocal here, like that, and that needs to be less than 1. So this is going to be limit as n goes to infinity of 2 to the first. Then there's an x left up there. N over n plus 1. Then there's a 2x left, less than 1. So this goes to 1. I'm left with 2. Absolute value of x is less than 1/2. Absolute value of x is less than 1/2. So my radius of convergence is 1/2. And my interval of convergence here is going to be -1/2 to 1/2. Let's test the endpoints. So if I have -1/2, then this becomes -1 to the n over n, which converges. X is 1/2, that's 1 over n, which diverges. So my interval of convergence is closed on the left-hand side at -1/2, open on the right-hand side at +1/2. Let's go ahead now and look at number 5. And number 5 says series as k equals 1 to infinity of -1 to the k over 10 to the k x minus 5 raised to the k. So let's use the ratio test again. Actually, let's go ahead and just use the root test here because everything is to the k power. So this is going to be kth root of absolute value of -1 to the k, x minus 5 to the k over 10 to the k less than 1. So forget about that part. This is x minus 5 over 10 is between -1 and 1. So -10, x minus 5, 10, add 5 to both sides, 15. Then let's go ahead and test that if this is going to converge on both sides because it either becomes 1/10 to the k or -1/10 to the k, which are both geometric, and the r of -1/10 or 1/10 is between -1 and 1. So let's go ahead and check that. Here. Sorry, misspoke. Stick in -5, that's -10 to the k. So that's a -1 to the k comes out, just becomes a 1. The 10 to the k cancels. Will just be 1 to the k. No, that diverges. The other side is going to be -1 to the k. When I'm done, that diverges. I canceled wrong in my head. So neither side converges there. That's open interval -5 to 15. The interval of convergence here is, I'm sorry, the radius of convergence here is going to be 10. I get that by isolating this absolute value here. And making that so before, so there's my r, and then I can set that up between -10 and 10. Solve that this is -5 to 15. Okay. Let's move forward to number 7. K equals 0 to infinity of 1 over k squared plus k, 3x minus 1 to the k. So I'm just going to do this, so it'll help later. Three to the k squared plus k, x minus 1/3 to the k, like that. And then I'm going to have limit as k goes to infinity of, and the denominator here I'm going to write as k times k plus 1. It's going to be 3 to the k plus 1, k plus 1, k plus 2, x minus 1/3 to the k plus 1. Reciprocal here, k plus 1, 3k to the k, x minus 1/3 to the k, less than 1. So we have limit, as k goes to infinity, k plus 1 cancels. And right in infinity. So this is 3k over k plus 2. And then I have absolute value of x minus 1/3 less than 1. So this becomes 3, absolute value of x minus 1/3 less than 1. Absolute value of x minus 1/3 is less than 1/3. So r is 1/3. X minus 1/3 between negative 1/3 and 1/3. So x is between 0 and 2/3. And let's go ahead and look what happens when I stick those in. So when I stick in 2/3, this becomes 1/3 to the k, with 3 to the k becomes 1 to the k over an equals 1 over k squared plus k. Just put the summation there. So I'm going to say that this is always less than or equal to 1 over k squared, which is a convergent p-series. So this converges by direct comparison test, that I found something that was always larger that converged. So this one has to converge. So if this side converges absolutely, that a negative 1 to the n over k squared plus k converges absolutely, because we just found out that its absolute value converges. So our interval of convergence is 0 to 2/3, closed on both sides. All right, let's go ahead now and look at number 9. Nine says summation k equals 1 to infinity of 2 to the 5k over 5 to the 2k x over 3 to the k. I'm just going to write this as k equals 1 to infinity of 32 to the k. That's an infinity. It keeps writing an oval, but over 25 to the k x over 3 to the k. I'm going to write this as k equals 1 to infinity Again, let's get this all in here. 32x, 25 times 3 is 75. All that's to the k power. I'm going to use the root test here and say the absolute value of 32x over 75 needs to be less than 1. So this is 32 over 75, absolute value of x less than 1. absolute value of x less than 75 over 32. So there's my r is 75 over 32. X is negative 75 over 32. 75 over 32. Putting negative 75 over 32 in gives me negative 1 to the k, which diverges. Putting 75 over 32 in gives me 1 to the k, which diverges. So my interval of convergence is open interval negative 75 over 32 to 75 over 32. Let's move ahead now to number 23 in the textbook. And we're going to look at re-indexing some series here. So first question is n equals 1 to infinity of n c sub n x to the n plus 2. And it asks me to shift the summation index so that the general form of the series involves x to the k. So I want this k to be equal to n plus 2. If that happens, n is equal to k minus 2. So we have infinity k minus 2 equals 1. K minus 2, c to the k minus 2, x to the k. And when I add 2 to both sides here, this is k equals 3 to infinity. K minus 2, c sub k minus 2, x to the k. Now the short way to do it, if your teacher lets you just look at it and do it, is I need to subtract 2 from all of the things that are n's on the inside and add 2 on the outside. That wouldn't shift my variable, but you can just leave the variable alone and do that. So this came down 2, this came down 2, this came down 2, this one went up 2, and that is the fast way to do it. But we're going to do the substitution the way that the book tells us to do it here. So that was 23. Number 25 is summation from n equals 1 to infinity of n cn x to the n minus 1 minus summation n equals 0 to infinity of cn x to the n. And they want us to write everything in terms of x to the k. So main thing I need to do here is on this left-hand one, k equals to n minus 1. So k plus 1 equals n. And then we have k plus 1 equals 1. K plus 1 is n. C k plus 1, x to the k, minus, and then this one is just a substitution of k's for n's because I already have x to the n. Like that. And so this is k equals 0 to infinity. K plus 1, c to the k plus 1, minus c sub k, x to the k, like that. Moving along to the next problem. 27 is summation n equals 1 to infinity of 2 n cn x to the n minus 1 plus summation n equals 0 to infinity six Cn x to the n plus 1. And it's really annoying that it does that. Okay. Let's go ahead and say k is equal to n minus 1 on the left-hand side over here, making k plus 1 equal to n. So in this one, I'll do my substitution here first. K plus 1 equals 1, infinity, 2 k plus 1, c k plus 1, x k. I'll leave this one alone for a second. Six Cn x to the n plus 1. So this is going to be k equals 0 to infinity of 2k plus 1 ck plus 1 x to the k. All right, now let's start working on this other one where k is going to be equal to n plus 1. So k minus 1 is equal to n. So k minus 1 equals 0 to infinity. 6 ck minus 1 x to the k. And this is k equals 0 to infinity. 2k plus 1 ck plus 1 x to the k plus k equals 1 to infinity. 6 ck minus 1 x to the k. So now I'm going to have to look and see that this one starts at an exponent of 0. This one starts at an exponent of 1. So I've got to bring out that first term by itself. So they both start with an exponent of 1. So that's going to be 2 times 1 is 2c, and then 0 plus 1 is 1, x to the 0. So that's just a constant, plus, and then common indices, k equals 1 to infinity, and then this is going to be 2 times k plus 1 ck plus 1 plus 6 ck minus 1 x to the k on the outside. All right, let's go ahead and look at number 29 next. And it is n equals 2 to infinity, n times n minus 1, Cn x n minus 2 minus 2, n equals 1 to infinity, and Cn x to the n plus n equals 0 to infinity, Cn xn. Since this is I think it's my last one of this type, I'm just going to go ahead and do the shortcut I was telling you about. I'm going to add 2 on the inside, subtract 2 on the outside. This is going to go k equals 0 to infinity. And this is going to be add to k plus 2, k plus 1, ck plus 2, xk. And then I'm going to bring the 2 on the inside here. 2, let's see, just do a substitution k's for n since I'm already x to the n. So k equals 1 to infinity, k, c, k, x, k. And then same thing here. That's already x to the n, so k equals 0 to infinity. ck xk. Perfect, everything's in terms of k. Now, this is starting at 0, this is starting at 0, this is starting at 1, so I got to bring everything up to 1 here. K equals 1. Let's write this over here. K equals 1 to infinity, and write this part, 2k plus 1, ck plus 2, and then minus 2k ck, and then this is k equals, so plus ck, and this is when x or when k is 0, this is c0, and when k is 0, this is 2c2, like that, and k plus 2, k plus 1, ck plus 2, minus 2k. I don't think I shifted anything there. Oh, right. So they factored out a ck. So c0 plus 2c2 plus k equals 1 to infinity of k plus 2, k plus 1, ck plus 2. And then you're going to pull out a -1 and be left with 2k minus 1 ck, and then that's an x to the k on the outside. All right, that is the last problem in this section. We'll come back next time and start talking about 6.2, solutions about ordinary points. Very, very powerful way to solve differential equations, and using what we did with Cauchy-Euler, usually where we let y equal x to the m, though we throw in the idea of a power series with it. So we let y equal a power series that we'll look at, and we talk about how to take derivatives of those things, and then go ahead and make the substitutions, and we'll get answers that will combine into functions that look like things like this, that have k's in them. Then we'll go ahead and or n's in them, or whatever. We'll solve for those constants if we can, establish a pattern for how the constants are going to repeat, and if we have any recognizable patterns for Taylor series, Maclaurin series, that type stuff from back in Calculus 2, where we recognize functions for, say, sine of x, cosine of x, e to the x, ln of x, those types of things. Then we'll try and make those substitutions back and write them as elementary functions. If not, we'll have to leave our answer as a sum or difference of power series for our final answer. So come back and we'll do probably lots of examples. Let me see how many examples from that. We're going to do We're gonna do 8 problems, probably from there. So we'll do those next time. See you for the next video.